This is the second part of lesson 3.4. In the first part, we looked at how we can use Pascal's triangle and with or without combinations in order to count things like paths to get places. In this part of the lesson, we're going to look at something called the binomial theorem, and we're also going to tie this in with combinations. So, what's the binomial theorem? Well, first of all, remember the binomial is a two-term polynomial. So it's always going to have those two terms. That's how we recognize it. In previous math courses, when you're confronted with expressions like a plus b squared, instructions would usually read expand and collect like terms, or expand and simplify. So a plus b squared means the squared is on the brackets, so it means the whole bracket times the whole bracket, a plus b times a plus b, and then we would use FOIL to expand that, right? First times first gives you a squared, outside times outside gives you ab, inside times inside gives you another ab, and then last times last equals b squared in this case. And then we combine those two middle terms, AB and AB, they're like terms, and you've got two AB terms. For higher powers, then we'd still have to expand. Unfortunately, we didn't have a shortcut for doing this. We already know that a plus b squared equals a squared plus 2ab plus b squared from above, and so we can use that as our starting point, but we still have to multiply that by the binomial AB, which means that we'd have to multiply a times each one of these terms, and we'd have to multiply b times each one of these terms. So we'd have to do 6 different multiplications, and we'd get what we get below. The first 3 terms came from multiplying by a, the next 3 terms came from multiplying by b, and then we'd collect our like terms up, and we'd get that 4-term polynomial underneath. Unfortunately, the use of this method to expand a plus b to the 6 is going to require a lot of time and space on a page, right? We would have to just keep expanding and expanding, and we've only gotten up to an exponent on this one. On this one here, we only got up to an exponent of 3. So we'd have to, if we wanted to get to 6, we'd have to do a plus b to the 4 first, and then a plus b to the 5, and just keep expanding it. Now, luckily there's a shortcut. It still requires some work, but much, much less work. So it requires us to use Pascal's triangle, which we've already talked about, and here's just a reminder of what it looks like, at least the first 2, 4, 6, 7 rows, meaning up to row 6, since the first row is considered row 0. But we could extend that to more rows if we needed to. The formula for the binomial expansion, in other words, the binomial theorem just talks about a binomial expansion, tells us this. If we're multiplying 2 terms together, a and b, n times, then we can use those different numbers along with combinations, or don't even need combinations. We could just go straight to the triangle and do it. So whatever the first term is, a, it shows up over and over again in each of the terms of this expansion. This dot, dot, dot in the middle just means, this dot, dot, dot here just means there's missing terms, right? Not that we are going to be missing terms, it's just in the formula, it's representing the terms that we haven't written out. And then the b, we put that into each of our terms of our expansion as well. And the only thing that changes in each case is our exponent. First, we start with an exponent of n on the a term, and then we do n minus 1, and then we do n minus 2, and then there's some terms missing, then we get down to 1, and we get down to 0. Anything with the exponent 0 is just the number 1, so that a term disappears in the last overall term. And you'll notice that as for the exponents on the b, it starts at 0, and then it goes up to 1, and then 2, and then there's some missing terms, but then you have n minus 1, and then you end up with the exponent n as the highest exponent on the b term as we expand this out. And as for the coefficients, we have n choose 0, whatever n is. So that's easy. Just, say it was 6, like we were just talking about there, then it would be 6 choose 0. Then we'd have 6 choose 1, 6 choose 2 for the next one, and then some missing terms, and we have 6 choose 5 for n minus 1, and 6 choose 6 for our last one. So we use this n over and over and over again. So again, that's theoretical, maybe a bit hard to wrap your head around until you see some actual numbers, so let's do it. So we're going to use this formula to expand a plus b to the 4. All right, so n is 4. I'm going to use the same highlighting here. N is 4. I used yellow for A and green for B. Don't need to highlight it, but I think it might help. So we have 4 choose 0 times A to the 4, B to the 0, plus 4 choose 1. Yep, going up, confirming that. A to the 3, B to the 1. And then I've got 4 choose 2. Oops, left out the C. 4 choose 2. A to the 2, B to the 2. Notice I'm reducing the exponent on A by 1 each time, and I'm increasing the exponent on B by 1 each time. And the 4 here is just my exponent, 4. And I'm going to keep going until I just run out of combinations. I'm up to 4 choose 3. Obviously, I'm going to have to stop when I get to 4 choose 4. A to the, going down, A to the 1, B to the 3, and then 4 choose 4. That's as far as I can go. A to the 0, B to the 4. Notice how, when you look at the exponents on the A and the B, they are always adding up to 4. If I add those two numbers together that I circled in red, they always add to 4. The reason they always add to 4 is because 4 was my original exponent. So they're always going to add to the original exponent. I can simplify this. And I could use Pascal's triangle. Basically, this 4, this exponent 4 is telling me look at the 4th row of Pascal's triangle. So if I didn't want to use combinations and I had Pascal's triangle handy, the 4th row is this one. So 4 choose 0 is 1, 4 choose 1 is 4, 4 choose 2 is 6, 4 choose 3 is 4, and 4 choose 4 is 1. So I could just use Pascal's triangle. Or if I didn't have it handy, I could type all these different combinations into my calculator. But I have 1, A to the 4, B to the 0. Anything to the exponent 0 is 1. I don't have to write this out. I'm going to just because it's the first time we've looked at it. But that's just 1, so multiplying by 1 isn't going to change anything. That's 4, A to the 3, B to the 1 can just be B, plus 6, A to the 2, B to the 2, plus, back down to 4, A to the 1, which I don't have to write the 1, B cubed, plus 1, A to the 0. Well, A to the 0 we already saw was just, or anything that exponent 0 is just equal to 1, B to the 4. I could have simplified it. I'll do a little bit more simplifying, which I could have done as I went along in this row I just wrote, but just to really finish off, I don't need the 1 out front, I don't need the 1 at the end, I can just write A to the 4. Second term, nothing to change. Same with the third term. Same with the fourth term. And then I don't need those 1s before the B to the 4 either. So that would be the binomial expansion of A plus B to the 4. So hopefully you picked up on those things I was pointing out. Now there's other twists that we could throw in there, though. We don't have to. A and B aren't always going to be A and B. A and B are going to be whatever numbers are in the binomial expansion. This is much more what we normally see, isn't it? So x plus 3, for example, where I'd think of my A value as x, and my b value is just the number 3. And so it would be, and n of course is 5 in this case. So it would correspond to the 5th row of Pascal's triangle. We know there's going to be 6 terms in the 5th row, so I'm going to expect 6 terms in my expansion. So it's going to be 5, choose 0, x to the 5, 3 to the 0. And then I go down by 1 for each of my, I go up by 1 by each of my r values. In the 5, choose 1 in this case. I go down by 1 for each of my exponents on x, my a term. I go up by 1 for each of my exponents on 3, which is my b term. So let's just write it out following this pattern. Okay, so that's the expansion. That's how it would look. Of course, then I have to simplify. So again, I could type any of these combinations into my calculator to get the numbers directly, or if I have Pascal's triangle handy, then I could just look at row number 5, which is this row here, 1, 5, 10, 10, 5, 1, and know what my coefficients are from that. I also will need to expand 3 to the 0, 3 to the 1, 3 to the 2, because these are just numbers, and they shouldn't be left just as numbers. So I'll need to expand all of those out. So I get 3 to the 0 just equals 1, and 3 to the 1 equals 3. And what do I have next? 10, 5, choose 2 is 10, I believe. I'm already forgetting. I think it's 5, 10, 10. Went too far, didn't I? 10, 10, 5, 1. Okay, so 10, x3, 3 squared is 9. 10 again, x squared, 3 cubed is 27. 5x, 3 to the 4 is 81, and 1, x is just 1 in this case. X to the 0 equals 1, 3 to the 5 is 243. Okay, so we're simplifying. Next step is now we multiply, we put all the numbers out front, and we just do a little bit of final tidying. So in this term here, I've got a 1 and a 1. Neither of those matter. In the end, it's just going to end up being x to the 5. I could write a 1 out front, but I don't need to. In the next term, I got a 5 times a 3. I multiply them together and stick it out front. So 5 times 3 is 15. So I put the 15 out front. That's important, that I don't just leave that 3 dangling at the end, because that looks really stupid. We want it to be tidy and nice. In the next one, we got 10 times 9. So I'm going to write a 90 out front. And it's going to be x to the 3. And then I got a 10 times 27 for the next one, so 270. And then I've got 5 times 81 for the next one, so 405. And for the last one, there's no x term because x to the 0 equals 1. It's just 1 times 243. So I just have the constant term 243. So there we have our expansion. That was, it may have seemed like quite a bit of work, but certainly less work than it would have been to do x plus 3 times itself 5 times and have to keep expanding and expanding. I believe that is the last example we have for this lesson. So, obviously, you need to take a look at the homework for this. You need to practice it on your own. You're going to see just, the examples didn't show anything. Actually, I'm not going to expand it all the way up, but I'm just going to point out one last little thing. What if we saw something like this? 2x minus 5 to the 7. And now that's a big one. It's going to be 8 terms, but let's just even think about what the first few terms would look like. So I'd have 7, choose 0. In this case, a is 2x, and I'd raise that to the exponent 7, and I'd have negative 5 to the 0. Then my next term would be 7, choose 1, and it would be 2x to the 6, and it would be negative 5 to the 1. Then my next term would be 7, choose 2, and it'd be 2x to the 5, and it'd be negative 5 to the 2, and then dot, 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 and so on. How is that going to expand out? Well, 7, choose 0 is just 1, like anything choose 0 is 1. This part here, 2x to the 7, I need to put that 7 on the 2 and on the x. So 2 to the 7 is actually equal to 128. 2 to the 7 equals 128. Don't forget to put that exponent on the coefficient inside the brackets. And then, of course, I'd also have the x to the 7 there. So that would expand into a big number there. Negative 5 to the 0 is still just positive 1. Anything to the exponent 0 is positive 1. The next one would be 7, and that would be, then I'd have 2 to the 6, which would be 64, x to the 4, sorry, x to the 6. Negative 5 to the 1 is negative 5, so I'd keep that the way it is. And then the next one would be, I think, 21, if I recall. And then 2 to the 5 would be 32, x to the 5. Negative 5 squared is going to be positive 25. Anything to an even number is, even exponent is going to come out positive. So to simplify, the first term would just be 128 x to the 7, because those two 1s when we multiply don't do anything. The next term is going to become 7 times 64 times negative 5. I'm multiplying these 3 numbers together, one of which is negative. So overall, I'm going to get a negative between these terms. 7 times 64 times 5. Let's just do that. Oops, not plus. 403,200. Oh, sorry, that seemed fairly high, and now I see why, because I didn't. 7 times 64 times 5. That seems more reasonable. 2,240. 2,240 x to the 6. That's what that all simplified down to, including the minus sign. I didn't put that in the calculator, but that was assumed. 21 times 32 times 25. 16,800. So we can still get really big coefficients. And so on. I only did the first 3 terms, but it was enough to illustrate some special things to watch out for. So don't get tripped up on those things. Good luck.